Hello, math enthusiasts! Are you ready for today's discussion? Come and join as we venture to the world of mathematics. For today's discussion, I will be teaching you and guiding you through four of the most essential techniques in solving integrals. These include logarithmic integration, trigonometric transformation, inverse trigonometric integration, and integration by parts.
Let's start with logarithmic integration.
Logarithmic integration. This is used when the integrand is in the form of derivative over a function. Here is the formula.
Let's try an example. To solve the integral of dx over x minus 2, we let u is equal to x minus 2, which means our du is equal to dx. So, the integral becomes integral of 1 over u du, and that gives us ln u plus c. Then, we substitute back the u, giving the final answer ln x minus 2 plus c. For the integral of x plus 3 over x minus 1, we simplify first by dividing the function. That's why we get 1 plus 4 over x minus 1. Then, integrate each part. The integral of 1 is x, and for the second part, we let u is equal to x minus 1, so that du is equal to dx, making it 4 ln u plus c. Then, we substitute back the u, and the final result is x plus 4 ln x minus 1 plus c. To solve the integral of 1 over x ln x, we let u is equal to ln x, so that du is equal to 1 over x dx, which transforms the integral into integral of 1 over u du, and that equals ln u plus c. Then, substituting back the u. That's why we get the final answer ln x plus c. For the integral of x cubed minus 2x squared plus 2 over x minus 1, we divided the polynomials, and that's why we get the x squared minus x minus 1 plus 1 over x minus 1. Then, we integrate each part. That's why we get the value of integral of x squared dx is equal to x cubed over 3. Then integral of negative x dx is equal to negative x squared over 2. Then integral of negative 1 dx is equal to negative x. And for the last term, which is the integral of 1 over x minus 1 dx, we let u is equal to x minus 1, so that we get the integral of 1 over u du is equal to ln x minus 1 plus c. Putting it all together, the final answer is x cubed over 3 minus x squared over 2 minus x plus ln x minus 1 plus c. To integrate 1 over square root of x, 1 plus square root of x, we let u is equal to square root of x, which means x is equal to u squared, and dx is equal to 2u du. So the integral becomes integral of 2u over u, 1 plus u du. The u's cancel out, leaving integral of 2 over 1 plus u du, which become 2 ln 1 plus u plus c. And substituting back u, which is equal to square root of x, we get the final result 2 ln 1 plus square root of x plus c. Next, trigonometric transformations.
In trigonometric transformations, we use this technique when integrating a powers of a sine and cosine. Also, in this technique, we often use our knowledge in identities. Here are the identities that needed to remember.
Let's try an example. To solve the integral of sine cubed x, we start by rewriting it as sine x times 1 minus cosine squared x. Next, we let u is equal to cosine x, so that our du is equal to negative sine x dx. This allows us to replace sine x dx with negative du, and integral becomes negative integral 1 minus u squared du. We integrate each term to get negative u plus u cubed over 3 plus c. Finally, we substitute back the u, which is equal to cosine x. giving the final answer negative cosine x plus cosine cube x over 3 plus c. To integrate sine squared x, we use the identity sine squared x is equal to 1 minus cosine 2x over 2. This turns the integral into integral of 1 minus cosine 2x over 2 dx. Then, split it into two parts. That's why we get 1/2 integral of dx and negative 1/2 integral of cosine 2x dx. The integral of dx is x, and the integral of cosine 2x is 1/2 sine 2x. Putting it all together, we get x over 2 minus 1 over 4 sine 2x plus c. To integrate sine squared x cosine cube x dx, we start by writing cosine cube as cosine squared x times cosine x, and use the identity cosine squared x is equal to 1 minus sine squared x. This gives us integral of 1 minus sine squared x times sine squared x times cosine x dx. Letting u is equal to sine x, then we get du as cosine x dx, which let us replace the variables. The integral becomes integral of 1 minus u squared times u squared du, which expand to integral of u squared minus u raised to 4 du. We integrate each term to get u cubed over 3 minus u raised to 5 over 5 plus c. And then substitute back the u, which is equal to sine x. Therefore, the final answer is sine cube x over 3 minus sine raised to 5x over 5 plus c. To integrate cosine cube x over sine raised to 4x dx, we begin by writing the numerator as cos x times cosine squared x and using the identity cosine squared x is equal to 1 minus sine squared x. This transforms the integral into integral of cosine x times 1 minus sine squared x over sine raised to 4x dx. Then, let u is equal to sine x so that our du is equal to cosine x dx. Now, the integral becomes integral of 1 minus u squared over u raised to 4 du, which splits into integral of u raised to negative 4 minus u raised to negative 2 du. Then, we integrate term by term to get u raised to negative 3 over negative 3 minus u raised to negative 1 over negative 1 plus c. This simplifies to negative 1 over 3u raised to cube plus 1 over u plus c. And substituting back the u, which is sine x, we get the final result as negative 1 over 3 sine cube x plus 1 over sine x plus c. To integrate cosine raised to 4x sine cube x dx, we write sine cube x as sine squared x times sine x, and use the identity sine squared x is equal to 1 minus cosine squared x. The integral becomes integral of cos raised to 4x times 1 minus cosine squared x times sine x dx. Then letting u is equal to cos x, then du is equal to negative sine x dx. So the integral becomes negative integral u raised to 4 times 1 minus u squared du, which expand to negative integral u raised to 4 minus u raised to 6 du. Then, we integrate each term to get negative times u raised to 5 over 5 minus u raised to 7 over 7 plus c. Then, substituting back the u, which is equal to cosine x, therefore our final answer is negative cosine raised to 5x over 5 plus cosine raised to 7x over 7 plus c. Next, inverse trigonometric integration.
In inverse trigonometric integration, we use this technique when an integrand matches a known inverse trigonometric derivative. We apply the matching rule.
Let's try an example. To solve the integral of dx over 16 plus x squared, we first recognize that it fits the standard form of inverse tangent. Therefore, we rewrite 16 as 4 squared so that the expression becomes dx over 4 squared plus x squared. Using the formula for this form, we apply the inverse tangent rule. So our final answer is 1/4 times arctan of x over 4 plus c. To integrate the expression 1 over x squared plus 6x plus 13, we begin by completing the square in the denominator. Therefore, we rewrite x squared plus 6x plus 13 as quantity of x plus 3 squared plus 4. Now, the integral becomes 1 over the quantity of x plus 3 squared plus 2 squared, which is direct match for the inverse tangent formula. Therefore, our final result is 1/2 times the arctan of x plus 3 over 2 plus c. To solve the integral of x squared over the square root of 9 minus x squared, we observe that the integrand involves x squared in the numerator and a square root in the denominator, which suggests that it may be easier to work with a known standard form. We recall that x squared can be written as 9 minus the quantity 9 minus x squared. We use the identity to break down the numerator into a form that matches the denominator, which allows us to simplify the expression. This gives us two parts, the integral of 9 over the square root of 9 minus x squared and the integral of 9 minus x squared over the square root of 9 minus x squared. The first integral fits the standard inverse sine form and it evaluates to 9 times the arc sine of x over 3, while the second integral simplifies to the integral of the square root of 9 minus x squared, which is a standard result and evaluates to x over 2 times the square root of 9 minus x squared, plus 9 over 2 times the inverse sine of x over 3. After subtracting the second part from the first, the final simplified answer is 9 over 2 times the arc sine of x over 3 minus x over 2 times the square root of 9 minus x squared plus c. To integrate the expression 2x plus 5 over x squared plus 4x plus 13 dx, we begin by looking at the denominator and take its derivative. The derivative of x squared plus 4x plus 13 is 2x plus 4. We notice that the numerator is close to this derivative, except the extra one. So, we rewrite the numerator as 2x plus 4 plus 1. We do this to split the original expression into two parts, one that matches the derivative over the denominator and one that is a constant. This allows us to write the integral as the sum of two separate integrals, one with 2x plus 4 over the denominator and one with just 1 over the denominator. For the first part, since the numerator is exactly the derivative of the denominator, we can directly use the u substitution. Letting u be the denominator, we integrate as the natural logarithm of the expression. For the second part, we complete the square in the denominator. We rewrite x squared plus 4x plus 13 as the quantity x plus 2 squared plus 9. Now that the expression is in the form of squared term plus a constant squared, we can apply the standard inverse tangent formula. This gives 1/3 times the arctan of x plus 2 over 3. By adding both parts together, our final answer is ln of x squared plus 4x plus 13 plus 1/3 times the arctan of x plus 2 over 3 plus c. To evaluate the integral of 3x minus 2 over x squared plus 2x plus 17 dx, we observe that the denominator is a quadratic expression, so its derivative is 2x plus 2. This isn't quite the same as the numerator, but if we try rewriting 3x minus 2, we can express it as 3 times x plus 1 minus 5. We do this to create a term in the numerator, 3x plus 1, that resembles the derivative of the denominator after completing the square. Then, we split the integral into two parts, one with 3 times x plus 1 over the denominator and one with negative 5 over the denominator. Next, we complete the square in the denominator. The expression x squared plus 2x plus 17 becomes the quantity of x plus 1 squared plus 16. The first integral with 3 times x plus 1 on the top is now in natural logarithmic form after substitution because its numerator matches the derivative of the denominator. The second integral with a constant 5 in the numerator and a perfect square plus a constant in the denominator is a standard inverse tangent form. This gives us our final answer as 3 over 2 times ln of x squared plus 2x plus 17 minus 5 over 4 times arctan of x plus 1 over 4 plus c. Lastly, integration by parts.
In integration by parts, this is used when we multiply two different types of functions together. Here is the formula. Always remember that we should always choose u using the Liat rule, which means logarithmic, inverse trigonometry, algebraic trigonometry, and exponential.
Let's try an example. To solve the integral of x times e raised to x, we use the integration by parts. We begin by choosing u is equal to x because this will become simpler when we differentiate it. Then, we let dv is equal to e raised to x dx, since exponential functions are easier to integrate. Differentiating u is equal to x gives us du is equal to dx. Integrating dv is equal to e raised to x dx gives us v is equal to e raised to x. Now, we apply the integration by parts formula, which is the integral of u dv is equal to uv minus integral of v du. Then, substituting everything in the formula, we get the integral is equal to e times e raised to x minus integral of e raised to x dx. We already know that the integral of e raised to x is e raised to x also. So the final answer becomes x times e raised to x minus e raised to x plus c. For this integral, we apply integration by parts as well. We choose u is equal to y because it gets simpler when we differentiate it. And we set dv is equal to cosine 4y dy, which is easy to integrate also. Now, differentiating u is equal to y, we get du is equal to dy. Also, integrating dv is equal to cosine 4y dy, we get v is equal to 1/4 sine 4y. Now, using the integration by parts formula, we substitute to get this integral, which is equal to y over 4 sine 4y minus integral of 1/4 sine 4y dy. We then integrate sine 4y, which gives us negative 1/4 cosine 4y. So, the final result becomes y over 4 sine 4y plus 1 over 16 cosine 4y plus c. To evaluate the integral of x ln x dx, we again use integration by parts. This time, we let u is equal to ln x because logarithmic functions are best handled by differentiating them. We then let dv is equal to x dx, which is simple algebraic term. Now, differentiating u is equal to ln x, we get du is equal to 1 over x dx. And integrating dv is equal to x dx, we get v is equal to x squared over 2. Using the integration by parts formula, we now substitute. So, the integral becomes x squared over 2 ln x minus integral of x squared over 2 times 1 over x dx. We simplified the expression inside the integral turning it into x over 2. Now, we integrate x over 2, which gives us x squared over 4. So, the integral result is x squared over 2 ln x minus x squared over 4 plus c. To integrate x times sine squared x, we begin by choosing a trigonometric identity. We know that sine squared x is equal to 1 minus cosine 2x over 2. Substituting this into the integral, we rewrite it as 1/2 the integral of x minus 1/2 the integral of x cosine 2x. So, now, we have to separate integrals. The first one is straightforward. The integral of x is x squared over 2. So, 1/2 of that gives us x squared over 4. Now, the second integral of x cosine 2x dx, we use integration by parts. We let u is equal to x, which gives us du is equal to dx. And we set dv is equal to cosine 2x dx, which integrates to v is equal to 1/2 sine 2x. Using the integration by parts formula, we get the integral of x cosine 2x dx is equal to x over 2 sine 2x minus integral of 1/2 sine 2x dx. The integral of sine 2x is negative 1/2 cosine 2x. So we now have x over 2 sine 2x plus 1/4 cosine 2x. We finally return to the original expression and combine both parts. Now, we have the final answer, x squared over 4 minus x over 4 sine 2x minus 1 over 8 cosine 2x plus c. To solve the integral of x squared ln x dx, we again use integration by parts. We choose u is equal to ln x, which becomes simpler when we differentiate. And we let dv is equal to x squared dx, which is easy to integrate also. Now, differentiating u is equal to ln x gives us du is equal to 1 over x dx, and integrating dv is equal to x squared dx gives us v is equal to x cubed over 3. Using the formula for the integration by parts, we substitute it into the equation. The integral is equal to x cubed over 3 ln x minus integral of x cubed over 3 times 1 over x dx. We simplify the integrand x cubed over 3 times 1 over x into x squared over 3. Then, we integrate x squared over 3, which results in x cubed over 9. So, the final answer is x cubed over 3 ln x minus x cubed over 9 plus c.
That's all for our video tutorial in integral calculus. I hope this helped you understand each integration technique more clearly. Thank you for watching. See you next time for our video tutorial. Bye-bye!